Why don't we get things rolling? I don't know why the good thing today is that everything fits on the screen for some reason. I don't know what exactly is up with the HDMI stuff. And we've seen this, of course, before. But today we'll finish off pipe flow, and I guess the last thing really to talk about, or two things, we'll talk about pipe networks, and we'll talk about making measurements of flow rates in pipes and how to do that. And the most challenging of those things is talking about pipe networks, and the only reason for showing this again, that we've seen many times before, is that, of course, this is a pipe network, right? The umbilical supplies some kind of backpack on the back of the person in the air, and it splits the flow in a Y or a T, and it comes out in two sides so that it's balanced, and you don't keep on going around uncontrollably in circles, I guess, if you had it just on one, coming out of one arm. And so pipe networks are an intrinsic part of what we probably want to look at in this class to finish off the things that we've been dealing with. So that's kind of what we will look at today, if I can find this, okay? And I might as well make this full size, and I might as well get rid of this. And so if we're looking at pipe flows, so the two things we'll talk about, and so maybe most of the time we'll spend time doing some examples, because I think that's the most useful part of this. Okay, is it connected? Yeah, it is connected. Okay, and so the main part will be talk about pipe networks, and the second part will be talk about flow rates, as we just mentioned. We can use the material that's in here to make the points that we need to make, and so pipe networks will be no different from anything else that we've done, in that what we need to use is we need to use our usual expression, which is the energy equation, Bernoulli equation, which just allows us to write behavior between upstream and downstream. And again, we've seen this many times, this standard expression. Morning, welcome. Downstream, pressure head, elevation head, pressure head, and velocity head, plus the sum of the head losses, both head losses which are major and head losses which are minor. And we know the form of these, we've seen it many times. Some coefficient, because we usually assume that it's turbulent in the fixture or fitting. A expression which doesn't make any assumption as to whether it's laminar or turbulent, because friction factor defines that, depending on Reynolds number. And the pump head that we put in the system is the power that is in the pump divided by gravity and the mass flow rate, which is density times volumetric flow rate. And so that's our basic expression. And so when we look at pipe flows, typically, they're typically on the same level. They're typically with defined behaviors at the ends of the pipes. And the components that might change in this, it's much easier, of course, if we have this issuing into a big tank. Because if we do that, then we can write the velocities at the end as being 0. So if we do that, then certainly for these points, the pressures would be 0. If we take points 1 and 2 as being on the top of this tank, then the velocities are also 0, so those drop out. And the only thing that is different is that the head loss, or the elevation difference in here, which is Z1 minus Z2, which are these two terms here, survive. And the only remaining component here are the head loss terms. And so in this particular case, where you could imagine that the head loss, if you plotted the head loss between upstream and downstream, would be something is going to change from one magnitude to the other, and that magnitude is actually going to be this height z1 minus z2. All that has to be figured out is exactly how that head loss will change between upstream and downstream points. So we know that the requirement for this from continuity is that the flow rates are the same. Continuity is just another way of writing mass conservation. In other words, V1 A1 equals V2 A2, etc. in all of these sections. And so all that's going to change is that the head losses, the cumulative head loss, which this will be, which we've done A to B before, this one here, is going to be the sum of all the individual ones. And so you could imagine that in the most open pipe, by definition, from this, the velocity is going to be smaller in this pipe than in this one, and in this one, etc. So the velocity is increasing as you go downstream, because the areas are decreasing and the flow rates have to be the same. And so you could imagine that if you parsed up this particular sequence of head losses, they would look something like this. They have to go through these final points, upstream and downstream, but the head loss in the downstream part will be larger because the velocity is going to be larger. And if it's turbulent, for instance, and the friction factor is constant, then V squared is actually going to increase faster than D will decrease, right? D will decrease because you're getting smaller, and so this will have, so this will increase. Well, actually, they'll both work in the same direction, right? So velocity will increase, and diameter will decrease, and so they'll both have the net effect of increasing the head loss. So we'd expect the head loss to look like this along the length of it. And so long as we know what the flow rate is along here, we can sum the individual head losses, where we can calculate exactly what the velocities will be because we can use continuity. And so that's for series flow within a pipe network. Really only one pipe, but it's just changing diameter. For the case where we have a parallel flow system, then the conditions are the opposite. Instead of adding together the head losses in each pipe have to be the same. In going from this, if we draw a circuit that goes through one of the pipes, which is this one here, and comes out here, and if we draw a circuit which goes through the lower pipe and comes out here, both of those streamlines have to have the same head loss attached to them because they have the same beginning and end points. And so the head loss between upstream for, well, we could actually draw it, I guess, right? We can draw the head loss versus distance, and it's going to look something like, it may not be linear, but for our intents and purposes, there is only one component. So this would be the head, and of course this would be the total head loss. And of course the total head loss actually is just this value here, right? So I'm slightly misrepresenting it. The head loss is just going to be the difference between Z1 and Z2. Just as before. And so if we go through pipe number 1 or we go through pipe number 2, the head loss will look exactly the same because it has to begin and end up at these 2 points, and it can only be the same. So in these particular cases, the head losses have to be equivalent to each other. And if we want to get the total flow through the system, clearly the total flow here is going to be equal to the sum of the two individual ones. Plus Qn, I guess, right? If there are n pipes. So we're not limited just to 2 pipes. So those are the two requirements that come from this. If we then look at the umbilical flyboards or whatever, the things we just looked at on screen, then the new behavior that we have for branch networks, in other words, a network that starts out as a single pipe but then branches into 2, we can rationalize again by drawing the flow paths through these 2 pipes separately, ending up at starting at A and ending up at B for one network, and then starting up at A and ending up at B for the second network, just as we usually do with Bernoulli. And I guess we know that one part of the network is in common for both of those flows. And so what we can do is we can write Bernoulli for each of those routes. The first route goes through the top pipe, goes through pipes 1 and 2 in this particular terminology. And so that is the velocity here. These are the velocities in the tanks, I guess, which are 0. So in other words, the energy equation number 1 is the top route. Energy equation number 2 is the bottom route, which has to start off. These parts here are all equivalent to each other, right? So the right-hand side is equivalent for both equations. The left-hand side is equivalent for both equations if it's written in the tank, because this is the atmospheric pressure, this is the velocity on the surface of the tank, and this is the elevation on the surface of the tank. So the second parts are also equivalent. And the only parts that are going to be different are going to be the head loss terms in each of the two components. For one of the components, the head loss in this has to be the same between each of these by definition, because it's the same quantity. And so if that's the case, then the head losses in these two final pipes, since everything else to the left of this is the same, so everything to the left of here is the same, so these have to be equivalent to each other. They have to be equivalent to each other because we both end up with the same head loss between the upstream and downstream. There's not much of a difference here, right? But that head loss would be this tiny amount here. This would be ZA minus ZB. And that's what this head loss has to equal. And so they have to be equivalent to each other, so hopefully then we can use those to figure out exactly what those magnitudes are. And presumably we're going to have to use something, well, depends what you know, I guess. If you know the flow rate through Q, then you just have to work out what the individual velocities would be by writing out the individual terms for the head loss, which would be friction factor, length over diameter, V2 squared over 2G for this one, which would be HL2, and HL1 would be, HL3 would be this one, and this would be squared rather, and that's going to be friction factor in 3, the length to diameter of that pipe, and the velocity in pipe number 3 squared over 2G. And so you need to be able to solve these to be able to honor this requirement that the heads are equal, head losses are equal to each other. So you could just write them as equivalent to each other and then attempt to solve that by knowing from continuity, and we'll do some examples. So these have to be equivalent to each other, but we also know that Q2 plus Q3 is equal to Q1. And so this can be written in terms of A2 rather, plus V2B3A3 equals Q, if you're given this, for instance. And so you need to be able to use some other constraint, just like we used in Bernoulli equation. We said that we need to have 5 knowns and 1 unknown. If we don't have that, we can't solve Bernoulli unless we have 4 knowns and 2 unknowns, in which case we can always use continuity to solve it. And so we're doing the same thing here. So that's the requirements, I guess. So all I was going to do for the rest of the time, I was going to leave 10 minutes to talk about ways to measure flow velocities and spend the rest of the time just doing a couple of examples to make the case. Typically, we've not on this midterm coming, but on the final, there's often been a pipe network question. And they they're moderately straightforward. They tend to get very difficult if you have, well, there's two examples we can show here. I'll go very quickly through the second one because as you'll see that it gets very complex in a hurry. And so just spend some time doing this. And so the idea here is to be able to solve for the network using what we just talked about. And I guess in this case, we have two tanks linked by either a branched pipe or a straight pipe. And the basic idea is if we have flow within the system occurring in just one pipe with this branch shut off, the question is if we add a third pipe to the branch, we want to add that so that the flow rate, instead of being flow rate with just one pipe, changes to being 1.3 times that flow rate. So by adding this pipe, we want to increase the flow rate by a specific amount, and it's probably asking what the dimension of the pipe is. So it's 25 feet above the tank. Determine the diameter of the new pipe and neglect minor losses. So minor losses would be at the T and inflow and outflow into the tanks, of course. So we're cut a break by being able to avoid those. And so I guess the first question is, if we have flow going through the system, what is the flow in the first case? We know what the head drop is between upstream and downstream. We know that this is 25 feet. And so we can write with a single pipe, where this one doesn't yet exist, we can write the energy equation. We write it from the tanks instead of the pipe because it gives us a break by being able to use zero velocities. And so upstream is this part, downstream is this part, and the head losses in the first pipe and the second pipe are given here along with their velocities. We know that the pressures are zero. We know that the elevations, this is going to be 25 feet, and this is going to be zero, if we just take the datum as here. And we know that the velocities are also zero, if they're big tanks. And so all we've got is that 25 feet is equal to the two of these. We know that since the diameters of these pipes are both the same, that V1 equals V2 by continuity. And so this V1 and this V2 can be put together to be able to define 25 feet, friction factor, cumulative length over diameter, and the velocities in the pipe. We know the lengths of each of those pipes, and the only thing that we have to figure out is the velocity. And so we can solve for the velocity, which ends up being 1.88 feet squared. This is the velocity here, 6 feet a second, and this is the volumetric flow rate. So we calculate the velocity from here by solving this expression. This is the only thing we don't know. We know that the flow rate is going to be the cross-sectional area in the pipe times that velocity, and so we can calculate what that volumetric flow rate is. And then we want to take that and multiply by 1.3 Q. And so 1.3 Q is just this amount here. And so now we're going to put a new branch in this, and we need to write the expressions to be able to define that behavior again. And so if we go back through pipes 1 and 2, it's going to be a higher flow rate now, but some of that flow is going to go not only in this pipe, but also in the other pipe. And so I guess we could think about it, the fact that we certainly know what the flow rate is in pipe V1, right? We've got that here. And so if we wanted to, we could certainly calculate the head loss between this point here and this point, because we know that the head loss in pipe 1 is going to be friction factor, length over diameter of pipes 1, and V1 squared over 2G. The V1 is not going to be the previous V1. It's not going to be this one. Whoops. But it's going to be a new V1, which will be 1.3 times that, because the cross-sectional area of the pipe hasn't changed, but the velocity, the volumetric flow rate has increased 1.3. And so if we wanted to, we could calculate this head loss to this point here, and then we could also calculate from the remaining head loss, which would be between this point and this point, the two flow rates, which would just be given by HL2 is equal to F2 L2 over D2 times V2 squared over 2G, right? So we would know the head loss that has to occur between C and B, because we know that it's going to be the head loss between A and C subtracted from 25 feet. So the remaining head loss we would know, and the friction factor we're given, and we know, I think we know it, right? So 0.02, that doesn't change. And so we know the length of the pipe, we know the diameter of that pipe, and we know the velocity squared. And so we'd know what we could solve for V2. Once we have V2, then we can calculate what Q3 would be, because we know Q and we know Q2, and we know that adding Q1 has to equal Q2 plus Q3, right? By definition. So we could calculate what the velocity would have to be in the pipe, and we could solve another head loss equation to figure out exactly what the diameter would be, which is the remaining part. Okay, so that's going back to say exactly what we need to do. So here's the working on that. So we can calculate what the volumetric flow rate would be, which is Q1, which is the new volumetric flow rate. And we know that Q1 and Q2 and Q3 have to equal that. We can write the flow going through the top circuit, which is exactly the same equation as before, which we had here, which is, this is going to be 25 feet. This is going to be the head losses in the two parts which are on this downstream part. So sorry, on the upstream and the downstream part. We have a velocity here in pipe 1 and a velocity here in pipe 2. And so we know what V1 is because we've calculated what it is through here, right? Because we know the flow rate. And V1 is this amount here. And the only thing that we have not knowing is the part that comes between this, which is the same as calculating what the head drop is between here and here, and prescribing that the flow velocity is conforms to that head drop. And so this equation here gives us exactly that, which is written by continuity. So we don't know what V2 is, but we know everything else in this equation. And as I said before, it's the same as calculating what the head loss is between upstream and C, and subtracting that from 25. And actually these two terms here, so 25 minus this term is exactly that head drop. And this head loss here conforms to that. And it's written in terms of velocity, so we can solve for V2. So now we know what V2 is that's coming out of here. If we multiply V2 by the cross-sectional area, we can get the flow rate that comes out of there. We know from continuity that this is prescribed, right? Q1 is 1.3 times our previous flow rate, and so we know this. We now know Q2, and so we need to know what Q3 is. So we can write Q3 as being the difference between those, which ends up being 1.03 cubic feet cubed per second. And now we can write the behavior between the upstream reservoir and the downstream reservoir, but going along this lower circuit. We know what the flow rate Q3 has to be. And so we can write this equation here. This is the energy equation. This has to be 25 feet. This is the head drops between pipe 1 and 3 on the bottom. upstream and then downstream on the bottom. We know what the velocity is in pipe 1, but we don't know, and we do know what the velocity is in pipe 3 as well, but what we don't know is this. And so we have one equation where we know 25 feet, we know what this term is, we know what this velocity is as well, because we just calculated a flow rate. And if we have a flow rate, then we know that the velocity 3 is equal to Q3 over A3. We know this. We know, actually we don't know this. So we have to write it in terms of that. And so if we write this expression where we know all the terms in this, the only term that we don't know is one that is the diameter of the pipe, which is 500 feet long. But also, I guess here, this velocity 3 is equal to also to Q over pi d squared upon 4. And it's the diameter of pipe number 3. And so that's what this term is here, which has been calculated, and you solve for D3. So it kind of involves, but the basic idea is if you winnow it down, is that we want to calculate the behavior without this pipe in it. So we can just do a flow circuit that goes through the top pipe, and we can calculate exactly what the flow rate would be by knowing what the head difference is, upstream and downstream. And the only unknowns are the two flow velocities in the pipe, which are identical to each other. So it's just one unknown. Once we have the flow rate known, we multiply by 1.3 to get the desired new flow rate. Once we have that number, we can calculate the flow in this pipe here, which is known, which is 1.3 times the previous one. And so essentially we can calculate the head drop between 25 feet to whatever it is here. And if we have that head drop on the final part, we can just calculate from head loss 2 being equal to friction factor length over diameter V2 squared over 2G. We know this. We know this. We know this. We know this. The only part we don't know is this, so we can solve for V2. Once we have V2, we know the flow rate through both systems is equal to the sum of the two components. If we know what this is and we know what this is, we can calculate what this is, and then we can write the third branch as being the head loss in pipe 3 being equal to friction factor length over diameter for pipe 3 and the velocity 3 over 2g squared. And the things that we don't know here are two things. We don't know this diameter and we don't know this velocity. If we knew the diameter, we could calculate immediately what this velocity was, and that would be an easy thing to solve, and that would give us, actually there wouldn't be anything left to solve. But in our particular case, we don't have the diameter, and the diameter goes both in the velocity term because we have a flow rate, and also in the friction factor loss term as well. So maybe not as straightforward as all that, but that's basically the way of doing it. So you have to be able to draw circuits through both parts. 3 reservoir problems. So these have been pretty nominally straightforward because we've known that the head loss on the downstream portion has been the same in both cases. So in both of these two examples, for a parallel system and for a system that has a Y that ends up in the same location, the head loss on both of these lower pipes have to be the same. They start with a common pressure here, they end up with a common pressure here, and so by definition the head loss has to be the same. If you end up with a system where all of a sudden now you have 3 reservoirs where the other 2 reservoirs are not linked, then you have a conundrum. And you have a conundrum because you don't know whether reservoirs A and B are flowing into C, or whether A is flowing, or B is flowing into both A and C, you have to make some assumptions about the flow network to be able to do it. And so I'm not going to go through this, but I will maybe talk about, in overview, how you do it, because it's actually moderately straightforward if you do it just at 35,000 feet and talk about it. And so first of all, you have to make an assumption about what the flow system is. And so the assumption here is that A and B flow into tank C. So A and B, which are both at higher elevation, 850 and 838 feet, flow into 805, which is at the bottom. And so we're basically making the case that this is the flow system here. If we do that, then we know certainly that QA plus QB is equal to QC from continuity. So that's the first thing that we can do. So we get one equation that describes that. And this, of course, can be written in terms of velocities. We won't do it, but it can be written in terms of velocities. And then we can write the energy equation in two different routes. We can go from A to C by going down here and along here and here. And we get an expression which is this, which is just the head loss between those two locations and the friction factors of parts 1 and 3, which is this. And so we definitely know this, but we don't know what the velocities are. We can write a circuit that goes from this tank here, from B to C, which is the next one, which would be the elevation changes between these and the friction factors or head losses in pipe 2 and pipe 3, which are these parts here. And then if we look at the unknowns we have in our system, we have 3. We have a velocity in pipe 1, a velocity in pipe 2, and a velocity in pipe 3. We have 3 unknowns and we have 3 equations. We have a continuity equation, which has those exact 3 terms in it. We have the first Bernoulli equation or energy equation, which has 2 of those 3 terms in it. And we have the second circuit equation from B to C, which has 2 out of 3 of the velocities in it. And so if we solve them simultaneously, then we get the velocities. It's not very easy because these aren't straight velocities. As you see, they're squares of velocities. And so you have to solve for the squares and dance around a little bit. But in conceptualization, I guess, the idea is that you have 3 velocities solved for, you need 3 equations, and you get those 3 equations by writing flow from A to C with 2 pieces of the network, flow from B to C with 2 different parts of the network, and those 2 equations have to be supplemented in the same way as we did it with Bernoulli when we're solving for 2 unknowns and we have only 4 knowns. We provide continuity, and that solves for the other component. Okay? So that's that. We have a bit more time. Maybe what I also put together was I actually grabbed some old exam questions. I don't ever want to teach this class to the exams, but they demonstrate the same thing. So in the last 3 years at least, I pulled, there's been a circuit question, and it's relied on the same kinds of things we've talked about here. I think it's probably much more straightforward than the things that we've just done now, because typically the way they guide you through them piece by piece. And so if you look at these questions, then they basically go through piece by piece. So in this particular case, you have a circuit. It flows from upstream to downstream. You know that the head loss in pipe 1 has to equal the head loss in pipe 2, by definition, because they start at the same point, they end up at the same point. We have a flow rate that goes through them, which we know, but we don't know how much goes through the upper pipe, and we don't know how much goes through the lower pipe. We have a roughness, and length of pipes, diameter of pipes. We have a loss in the pipe which is due to the pump, which you're given, which is 1.5, and it walks you through it. So what's the head loss in the top pipe? Well, certainly we can do that. It goes through pipe number 1, and it's equal to the length of the pipe, diameter of the pipe, velocity squared. The head loss in the lower pipe is exactly the same, but written for the lower pipe, but with this minor loss within it as well. So those are the two head losses. And so ultimately what we're going to want to do, since we know the head losses, we're going to want to be able to solve for the values of the different velocities, V1 and V2. And we'll know that the total flow rate through here has to equal to the sum of Q1 and Q2 by definition. So we know that that is going to be the case. So solve for the volumetric flow rates in the two pipes if the friction factors in both pipes are known. So we could write the between points 1 and 2 in the system. This is going to be equal to this expression here. And so this is the energy equation upstream plus the pump, the energy equation downstream plus the head losses in the system. We can write that the volumetric flow rates have to satisfy continuity. And so by that definition, and we can also write that the head losses between upstream and downstream have to be the same. We have to write this for, so this is wrong, actually, right? This has to be written for one circuit at a time. And so if we do that and rewrite this, the only term that we have in this, if we define these behaviors, are going to be these velocities here, which we don't know. And so this is the equivalent head losses between upstream and downstream. This is the upstream, this is the upper flow line, which has a head loss. This is the lower flow line, which has a head loss given by its velocity in the upper pipe and the velocity in the lower pipe. And so we have one equation, but we have two unknowns. We know the friction factors are the same, we know the lengths of the pipes are the same, we know the diameters are the same. And so all we need to solve for is the value of the velocities relative to each other. So we could solve for V1 as a function of V2, or the converse. And so we can solve from this for V1, which ends up being this expression here. And if we know then from continuity that Q total is equal to Q1 plus Q2, which is the same as V1 A1 plus V2 A2, then we know the areas, we know what this is, and we know what these are relative to each other. And so we can substitute, say, for V1 in this particular case and get the behavior in terms of V2. We know what Q is, and so if we can write these, we could solve this for V2. And so in this particular case, the flow rate coming out of V2 is this. If we know what V2 is, then we can calculate that Q1 is equal to Q minus Q2. We know what this is, it's prescribed. We've just calculated this up here. And so it's just a matter of solving that expression. And finally, if we want to calculate what the head loss between upstream and downstream is, we can just use either one of the circuits, either the upstream or the downstream. They should be the same as each other, and calculate exactly what the head loss is coming out of the system. So I put a couple of others in there, and they end up. This one ends up being almost exactly the same as the other one. This looks almost like a three reservoir problem until you realize that you're told in the question that these elevations are the same. So it's just the same as being a single reservoir. So it's no different from that. And so it's not a three reservoir problem that you have to solve the squares of three equations. It's just the same as a single downstream tank. You could draw this just as the same tank, right? And so those are there. And yeah, they start repeating each other. So these are from 2018, 17, and 16. And so not for this coming midterm, but the final exam hasn't been written yet, but they've occurred reasonably frequently. All right, so 10 minutes left. The other thing I was going to mention, which we said we'd talk about flow networks, and we'd also talk about measuring methods of measuring flow. And so typically, when you buy gasoline, for example, or where you get fluids metered into your house and pay for something, sometimes it's useful to know exactly what the flow rates are, and for a whole host of other reasons. And there are basically three ways to be able to measure flow rates. One is that you can constrain flow and measure a proper pressure drop between upstream and downstream, the Venturi type flow meters, which we've talked about when we talked about Bernoulli, for example. You can use the flow to balance momentum against something. So if you imagine putting an impeller within the flow stream, the forces on that impeller will turn it, and if you can measure the rate at which that impeller moves, you can use that to measure flow rate. Or you can pour your gasoline into a bucket and then pour it into your car. So you put 10 bucketfuls in your car, 10 gallons, and you've metered it in that way. And you can do that in more sophisticated ways. So those are the three basic ways of doing it. And so we can talk about each of them in turn. I suppose if you talk about constricting flow and measuring pressures between upstream and downstream, then I suppose the issue is that you'd like to have a constriction in here that gives you a predictable flow at all flow rates, all Reynolds numbers. And I suppose you don't want such a huge constriction that you spend all of your energy pushing the flow through there because of the big head loss as you get across here. So you'd like it to be a low head loss, which means that you probably don't want much of a constriction. But of course, if you have a really low head loss, then your resolution of being able to measure the pressure differential is going to be tough. And so there's a balance between each of those. And so we've talked about the equations for flow meters before. Basically, what you want to do is be able to calculate a volumetric flow as a function of a pressure drop. And you can just write the energy equation or Bernoulli's equation between upstream and downstream, where you have this constriction in flow. And ultimately, if you can measure the pressure drop between these two locations, if you know what the density of the fluid is, if you have some correction factor that says something about the geometry of this orifice and how it departs from ideal conditions of an inviscid fluid, for instance. Ideal means viscosity equal to 0 is what we're calling ideal. In other words, the requirements for a Bernoulli equation are that it's an inviscid fluid. And then you can calculate what this correction factor is as a function of the flow rate. And so because typically fluids are not ideal, then if you want to apply this correction, you can do it by running experiments at different Reynolds numbers. And so if you look at this chart, you see that this correction factor that you're applying varies as you increase the Reynolds number. And so you need to know the Reynolds number to be able to calculate what that loss is. But you see immediately that the range of this is really not very high. Right? This is about 4 in 6, so it's less than 10%. It's about 8%, is it? Something like that. So this is only about, varies by 8% in this full range. And of course, for the constriction, which is largest, so D over D rather, when it's equal to 0.2, that means that this is very small, compared to the diameter, so a big head loss. But for that particular case, it's almost constant with Reynolds number, which is probably good, because then you don't have to know what Reynolds number is to be able to make the measurement or correct for it. It's bad because if you're pushing it across this boundary, then probably you have a big head loss that does it. But this 8% is really not, it might be a lot if you're buying gasoline, I suppose, but it might not be so much if you're measuring less valuable fluids. If you want to make a less disruptive flow, instead of having a plate in the flow that would have these eddies that exist behind it, you can make a Venturi type meter which has a smooth transition. And you see that if you do that, then this correction factor then changes again to range only by something like 6% in this particular case, but and again be relatively flat for some portions of Reynolds numbers. But by making it smooth, it becomes that the correction is very close to an ideal fluid, an inviscid fluid. And so you can design your flow meter, if you like, to have as little disruption as possible. And I guess the ultimate evolution of that is to use a Venturi meter, where now the flows, as you go downstream, cause no eddies to form at all. You're just hugging the pipe. And so it's kind of a laminar flow with the deck of cards, the laminae of fluid just skidding over each other. And in that particular case, again, the range of these correction values, again, is of the order of a few percent. Varies with Reynolds number, once again, and you measure pressures in the unrestricted portion of the flow meter and in the maximum constriction of the flow meter. And if you know what the magnitudes of those two pressures are, and if you know what the density is and what any correction factor is, constriction magnitude is rather, this is d over d, and then you can know the upstream cross-sectional area, and if you know this correction, then you can calculate what the flow rate is. That's basically the idea. So those flow meters are useful because they have no moving parts. The other two that we talked about are balancing forces, and so I guess the example of that, I actually looked it up last night. Let's see if I can find it again. Tire pressure gauge, see if they have some figures. It's probably not a bad one. Actually, this is one that's pulled apart. So a pressure gauge, and so the idea is you put the nozzle on the valve on a tire. The air comes up here, it blows down here, and there's a plunger that, it's actually showing it animated above. The air, you put it on there. The air comes out of the valve. Just going to do it. It fills up this. It pushes the plunger down against the spring. And so it's this pressure which is acting against the spring. And the higher the pressure, the more it will compress the spring. If you know what the spring constant is, or if you calibrate it, you can figure out that a higher pressure will compress the spring more. And so the amount of the tire pressure gauge that comes out of the system is directly proportional to the pressure that's being applied against it. And so that's not so different from having a system where you, for instance, have an impeller. And so other ways of looking at this would be having a bead within a flow, and the bead gets acted upon by the flow that's going past it. It'll have a drag that's attached to it, and the finite weight of this will act against that drag. And you could imagine, we'll start talking about it next week, that the drag force is the same as P over rho v squared. This is the Euler number, right? And so this is the coefficient of drag, because the Euler number is a non-dimensional magnitude. So this is a coefficient, a non-dimensional coefficient. And if we write a force as being pressure divided by area, or force over area is the same as pressure over rho v squared. And so if you know what the weight is of this bead acting downwards, you know what the forces are that are acting on this if it's sitting there. It has to be in equilibrium. It has to be equal to the weight of that bead. And so if you know this drag coefficient, which is just a number, and if you know the area, cross-sectional area of this, you know the density of the fluid that's flowing, the only thing you don't know is the velocity. And so you can solve for the velocity. And so that's one way of thinking about transfer of momentum onto the fluid onto this static component. And the other more elegant version, I guess, is to think about an impeller with inflow. And so here you just have a propeller, an impeller. Flow goes past it. It's the same process, right? It's transferring momentum from the fluid onto the impeller. The impeller rotates. And if it rotates, say, in a magnetic field, you can get an electric signal out of it on the outside without having contact with this that will measure the number of rotations of this that occur. And so that's the other way to be able to do it. So again, an exchange of momentum. So tire gauge, the bead that's held within an airflow, and also an impeller. And the final one is being able to measure how much volume you put in a bucket. And so the more elegant way of looking at that is to look at the so-called nutating, N-U-T-A-T-I-N-G valve, which basically has a coin in it on a vertical spindle, and the coin, if you like, is off angle, and that coin spins around on this axis as you flow fluid into this chamber. The fluid goes in, it gets caught underneath this nutating disc, and it delivers a set volume out of the downstream end as it rotates through one dimension. It's almost, you could almost think of it as being a flapper that fills up and then discharges downstream. Fills, discharges downstream. And it really isn't all that different from taking a bucket, filling a bucket, and then putting it into a tank, filling a bucket again, and repeating it again. Except that this has the nutating disc does not rotate, it just flips backwards and forwards to be able to meter out this set amount of volume as it goes down. And I suppose the other component of that behavior is, I've never quite worked out how these work, but you see these outside all the apartments in town. These are gas meters. And a gas meter, somehow it takes a volume of gas into a chamber that changes its volume to accept the gas. It automatically flips a valve, opens up the outlet for it, and allows that metered volume to flow into the house, and then repeats this. So it's kind of a closed volume that allows you to fill it up with a fluid, in this particular case a gas, and then allows that metered volume to go from the upstream part to the downstream part. So a little bit like a nutating disc. So right on time. So that's it for today. So the first of our 3 recipe topics is now done, I guess. Flow in pipes. So both flow in individual pipes and now in flow networks, where friction losses are the essence of what's going on. Next week we'll be in class and we'll talk about external flows, which are similar to pipes but on the exterior pipes. And then after Thanksgiving we'll talk about flows in open channel flows in conduits, rivers and streams. Okay. All right, thanks very much.